now the next pattern of biodiversity which we are going to talk about is species area relationships. Okay, so as the name suggests, it is going to be some sort of relationship between the species and the area where they live in. So basically this will give us a relationship between species diversity and the area. Now, before we talk about the equation which gives us a relation between the two, we should be clear about what do we exactly mean by species diversity. Now, species diversity basically talks about the richness of species. That means how many different species exist in a particular area. So, the species diversity basically includes two terms. One is species richness, which means what I said just now, that how many different species are existing in one area. And the second one is species evenness. Now, what is species evenness? That means how evenly the number of organisms in each species are distributed in that particular area. So, species richness and species evenness, these two together constitute species diversity. So, now what has been observed so far is that in a particular region, in a particular area, the species richness increases with the increase in explored area. Now, what do I mean by explored area? Now, let us suppose if I talk about a particular region. So, when I say a region, I mean there is no particular limit. So, I decide my limit to define a region. So, let us say this is my region. Now, initially, this is just an example. So let us say initially there were organisms which were living only in this much area of this entire region. So they were not, the organisms were not living everywhere. So the species diversity could be seen only in this area of the region. So you found different types of species or different types of organisms in this area. But gradually one or two organisms moved out of this boundary and they started exploring new areas. So gradually the species diversity could be seen in this area as well. And this could continue. Right? So as new areas get explored, species go and start living there. So organisms basically go and start living there. And that is how the species diversity increase in a particular area. Now you would have seen this in case of human beings also. Now some of the cities which were not very developed earlier, so they gradually develop. So what happens? Initially maybe a lot of open area was there. Now gradually when the population in that city increases, so more and more people need houses to live. So what happens? They start exploring the open area or the empty areas, and that's how those empty areas also gets overpopulated. So a similar concept applies to this species area relationships as well. So this means that the species diversity will increase, that is, it will be directly proportional to the explored area in some way. Now, what is that some way in which they both will be related? That is what we will see in this species area relationship equation. So, the equation is somewhat like this. The equation says log S is equal to log of C plus Z log of A. Now, you might be quite surprised that from where so many things came up, S, C, Z, A, and we were just talking about two things. S, that is species diversity, and the second was A, that is the area. So let us see what are these. Now, as I said, that the species diversity. Now, here the species diversity is mainly denoted by species richness, which we have denoted as S. So S is directly proportional to A. A is the area explored. Now, but this directly proportional will continue only up to a certain limit. It will not be forever. It is not that it keeps on exploring more and more area and the species diversity is increasing. Now, as it reaches a certain point, the diversity of the species doesn't increase any further. That's because there are other factors also which governs the species diversity. Right? We have seen that there are climatic factors, there are availability of food, availability of water. There are so many other things which actually determine the species richness in a particular area. So, but Up to a certain limit, as area increases, that is as explored area increases, the species richness also increases. And how are these two related? They are basically related in this way. Now whenever you convert the proportionality into equality, you need to give a constant. So that constant is C, and it has been observed that the relation between S and A is exponential. So this is CA to the power Z. So this is the actual relation between species richness and the explored area. So what do we see here? So here you actually see that in the same equation, if you take log on both sides, you will get log S is equal to log C plus Z log A. So this is what you will get, and this equation is the same as this one. Now what is C here? Just now I said C is the constant. So C is a constant here. And what about Z? Now we will try to understand what is C and what is Z and what is their significance in this equation with the help of graph. So that the graph will help you to understand it better. So let us try to understand the species area relationships graphically. Now here on the graph we have taken the species richness, which is denoted by S on the y-axis, and we have taken the area, that is A, on the x-axis. Now what kind of a graph do we get? As I said, now as area increases, so as the value of A increases, the value of S also increases, but this increase happens only up to a certain limit. So the graph which we get is somewhat like this. So initially as A increases, S also increases, but after a certain point it doesn't increase any further. So, and this curve also tells us the exponential relationship between S and A, right? Now as I had mentioned just now, that S is equal to CA to the power Z. Now if we take log on both sides, it becomes log S is equal to log C plus Z log A. Now here the graph which we have plotted, we have considered this equation, where that is why we get an exponential curve, right? Now what will happen if we try to plot the graph between log S and log A? So in that case, how our graph should look like? Any idea? Now let us try to look at this equation in even more detail. So let us say if we want to plot a graph where instead of taking S, we take log S on the y-axis and we take log A on the x-axis. So in that case, basically log S is our y and log A is our x. So in that case, what happens? The equation is of the form y is equal to mx plus c. And what is this equation? This is the equation of a straight line. So this shows that if we plot the graph between log S and log A, we will get a straight line. So let us try to do that. So let us suppose we plot the graph between log S on the y-axis and we take log A on the x-axis. So in that case, what kind of a plot will we get? We will get a straight line. So this is going to be a straight line. Now in this straight line, in the general equation of a straight line, what is M and what is C? M is nothing but the slope of the line, and what is C? C is nothing but the y-intercept. Now, I hope you would have learned it in your mathematics, but in case you have forgotten the concept of equation of a straight line, let me quickly remind you. So it is somewhat like this. Let us suppose this is your plot. So if this is your x and if this is your y coordinate, and if you have a straight line like this, then this is the y-intercept. So if you see this line touches or it passes through the y-axis at this point. So this value is C. This is known as the value of y-intercept. And what is slope of the line? Slope of this line will be given by tan theta. So tan theta is nothing but this value by this value. Right? So this is about the slope and the y-intercept. Now with this, you will be able to understand what is C and what is Z. So basically Z is nothing but the slope of this line. So slope of this curve is denoted by Z. And what is C? C is nothing but the y-intercept of the straight line. So now with the help of this equation, you can actually analyze the relationships between the species richness and the explored area of a particular region. So now it has been observed that the species area relationships is almost constant for areas in a particular geographical region. That means, as I said, let us suppose if I am considering a particular region. Okay, so in this region, if you calculate or if you look at the relationship between species richness and area, in this area and again in this area, again in this area, in this area, so you see that the relationship between species and area in all these 4 areas within a particular region are almost the same. So that was one observation as far as species area relationships were concerned. The next observation was that this particular relationship can actually give you a lot of information about the relationship between the species richness and area of a particular area. It has been observed that for a larger area, the slope is larger. That means the value of the slope. So if you are trying to analyze the species area relationship of a larger area, so in case of a larger area, the slope, and what is slope? Slope is nothing but the value of Z. So Z is going to be larger. So a larger area has got a larger value of Z. Now what do I mean by a larger slope? Larger slope would mean if this is your graph, so larger the value of the slope, the more steeper the graph would be. So this will have a larger value of slope. If you have a smaller value of slope, so it will be like this, because as theta increases, the value of slope increases. That means the value of Z increases. So for larger area, you have a larger value of slope. That means the theta is more, which means that the graph is more steep. So the slope is steeper. Whereas if the same species area relationship is analyzed over a smaller area, just the vice versa happens. That is, the value of the slope is smaller and the slope is less steeper. Now, why does the slope steepness changes with the size of the area? That's because when you are considering a very large area, there the species richness is more. That is, more variety of species are existing there. So in that case, what happens, even as the value of your x changes a little bit, the change in your y is quite more. That is, the species richness is more when compared to the change in area. Therefore, your slope is steeper. But in case of a smaller area, it is more proportional. That means when there is an increase in the in case of a smaller area, what happens is as the area increases, the species richness also increases. But the way the value increases gives it a less steeper slope. So I hope this concept of species area relationship is clear. Now the concept is quite simple. You just need to know this relationship. Now once you know this, all you have to do is just apply the concept of equation of a straight line to this equation, and you will be able to analyze or interpret the results really well. Now the question is, what is the importance of this species area relationship equation? What do we do with this? Now it actually helps us to predict the number of species in a particular region. Now let us suppose it is not an easy task to go and calculate and describe each of the species which are found in a particular area. So with this calculation, it gives us a rough idea about the number of species which exist in an area in a particular region based on the area, if not much information is available. Like it is not always necessary that it is very easy to go to a particular region and then investigate the area and all the living organisms and then calculate the number of species in that area. So that is not an easy task. So if you want to get some idea about the number of species, if you know area, you can make use of this equation and you can get a rough estimate of the number of species in that particular area. So these were the two concepts which help us to give and to get an idea about the variation of biodiversity. One was latitudinal gradient and the second one was species area.